So if you haven't watched before, this is John Nelson, our Senior Applications Engineer. Any of you have watched any demo days? I think you've been in every single one of them.
Yeah. How a UMC is built, I wasn't in.
Yeah, you missed one.
Yeah.
Okay, so you've been with Haas for about 20 years.
Yeah, next month, 20 years.
Okay, and 12 of those, is that what you said, were in an applications role?
Yeah, for 12 years I was either an applications engineer or managing that applications department.
And how many times have you heard people say, Haas can't cut steel? And yes, that's how you all sound in my head.
Yeah, we have definitely heard that before. As the applications department is the group that's responsible for helping Haas customers use their machines. And there are a lot of people who have contacted us about having trouble cutting steel on their Haas machine. But it's not because the machine wouldn't cut steel, it's because they were not running at the correct parameters for that machine, right? You've got, there's a mini mill that's a 7.5 horsepower spindle versus this VF2YT that's got a 30 horsepower spindle. Right. So there's a big difference, right? This has 3 times the torque that machine has. You can't take the same cut in steel on this machine as you can on a mini mill. It's that simple.
And then the last demo of the day, we're actually on a 60 horsepower machine.
Yeah.
So even a step up from here. And we were talking a couple weeks ago, there was an application, there was a customer that had a, I don't know, a 3 or 4 inch shell mill on a tool room mill trying to take a massive cut, and he couldn't figure out why the machine wouldn't do it.
Yeah.
And that's exactly what you talked about. You got to have the right machine for the job.
Exactly. We get a lot of complaints about cutting aluminum, that another aluminum demo from Haas, or people saying it at trade shows. But there's a bunch of reasons why we actually cut a lot of aluminum. A demonstration is really kind of like a television commercial. You got a limited amount of time to grab somebody's attention, and aluminum demos are impressive. The spindle speeds are high, the feed rates are fast, the chips are flying all over the place. Aluminum demos are interesting to watch. That doesn't mean the machine can't cut steel because we're showing aluminum, obviously.
And there's another good reason for it too, and that's the amount of times you need to change your tools.
Yeah, absolutely. At a 8-day trade show or something, you go through a lot of tooling cutting steel on a demo, because in the Haas booth we cut all the time. Yep. We're always cutting parts. When the operator finishes a part, they put another one in. There's no sitting there waiting for it or shadow cutting. We don't do that very often at all.
Right. So, okay, we've talked about we can cut steel. We're about to show people to cut steel. One of the things, we talk about horsepower, and you and I just talked about it, but one of the things that comes into play when cutting steel is torque. Yeah. And we're going to talk about that a little bit today.
The most important thing is for somebody, if you're having trouble cutting steel, is to understand what model of machine you have, what spindle that machine has in it, and what the torque and horsepower capabilities of that machine, of that spindle, are. Right. We have torque charts displayed on every machine model on our website. They're very easy to see. Andrew's got
I've got it pulled up here, actually, if you want to take a look at it, Frank. So we got the VF2YT here, same machine that you guys have got over there. And so if I, here on the website, if I just page down a little bit, and I go down here kind of to the right, I can see that I have this torque chart. I can just click on that, and there we go. So actually, I'm going to just bring up this version here because it's a little blown up. Same chart. So here is the torque chart for this particular spindle on this machine.
Yeah, you'll see along the bottom is the RPM. So this is the first thing that you need to find on that torque chart. What RPM are you running at? The blue line here is horsepower. And you can see that at very low RPMs, there's not much horsepower at all, because it doesn't take a lot of power to get the spindle turning at 500 or 1,000 RPM. But what it does take is a lot of torque. So we can take that power that we're not using to make the spindle rotate quickly and turn that into torque. So we have maximum torque at low RPM, and that's the dotted line up here. So you can see that our maximum torque on this particular machine is right about 90 foot-pounds of torque. So the foot-pounds are listed on the left-hand side of the chart. The horsepower values are listed down the right side, and along the bottom is RPM. So you find your RPM and then see what torque and horsepower you have at that speed. Don't forget to verify the machine models and the spindle type at the top of this torque chart. On the torque chart for this particular machine, you've got the first chart you're going to see is I guess in imperial units, right, using horsepower and torque in foot-pounds. But if you scroll down one, you'll get the, I guess, metric version, where we have the horsepower in kilowatts, actually, the power in kilowatts, and the torque measured in Newton meters. Right. So that's the difference between those. And if you go down again, you'll see the torque chart for this machine with a gearbox. So we have four sets of torque and horsepower lines on this. One of them is the low gear values. The other set is the high gear values. And you can see where the shift point is there. So that's torque chart.
And if you're really doing heavy cutting, you may want to consider doing a gearbox machine, because you can see you've more than doubled your torque at low RPM.
Yeah. So this machine without the gearbox is 90 foot-pounds of torque peak. And then this machine is 250 foot-pounds of torque, so there's quite a bit more. If you're cutting hardened materials, if you're cutting tough materials, stainless steels, titanium, you definitely want to get a gearbox machine. It doesn't mean that you can't cut those materials if you don't have a gearbox. It's just that you can't cut them as efficiently as if you had a gearbox. And we will get back to, after our demonstration, we're going to measure the spindle load values of each of the cutters in our demonstration, and then we'll go back to the torque chart and show you how those values relate to the torque and horsepower curves in the torque chart.
Okay, the other thing we're going to do is we're going to go through each tool. Now, each of these tools is from HaasTooling.com.
Yes.
So we're going to talk about feeds and speeds. Andrew, do you mind pulling up the HaasTooling.com?
Yeah, okay, so from the website, if I go over to the right side of the screen here and I hover over Haas Tooling, this gives you access to all the various menus for the different kinds of tooling that we sell. I've already clicked on the milling section here, and I can see I've got milling bodies, inserts, end mills, all that sort of stuff. Now I've got another tab open. Here's milling inserts, and this is going to get us close to where you're starting off with, right, John?
Yes. So tool number one in my demonstration program is the 3-inch face mill. It's got the 45-degree inserts here. It's a 6-flute face mill, and we've got the speed and feed chart up there, and I've put a red box around the different parameters that I'm using in this demonstration. You can see I'm cutting an alloy steel over here on the left. I'm using the HMP 35 inserts, which are the preferred grade for steel. And I've programmed it at 850 surface feet, which is right in the middle for a spindle speed. And the feed per tooth feed rate is 10 thousandths, actually just a hair under 10 thousandths, which again is right in the middle of the recommendation. So the point is to show you that if you get these tools from HaasTooling.com, plug in the numbers, if you got all the parameters right, you're going to be right in the ballpark. You'll be able to make those cuts, assuming you've got the amount of torque that's required for that cut. You'll be able to take that cut and then optimize for your particular application if you need to speed up or slow down.
So Andrew, you want to show them how you get to those?
Yeah, so let's go. I'm back now on the main milling inserts page, and I don't have your exact one here pulled up, but let me just click on any one of these because this will just show us. So I click on the insert. Takes a moment.
Of course,
maybe I should have had that opened already. There we go.
Perfectly yesterday.
So here's in the insert page, and down here you can see technical specs and stuff like that. But what I want is this speed and feed. It's kind of hidden away here. But if I click on this, this will bring us to the same chart that John was just showing, except that John's version that I have here is highlighted, of course. I'm just going to click back over to that. He's got the actual values that he's using highlighted, but you can see it's just a couple clicks away to get the information that you need.
Okay.
So back to you, John.
Yep.
So the second tool in this program is the 3/4 inch 4-flute end mill. This is the standard length end mill, 4 flutes, and Andrew's got it pulled up over there. The surface footage that I programmed is 575 surface feet and 4 thou and 4/10 feed per tooth. On the depth of cut, we're going nice and deep at 1.5 times diameter, and I'll talk a little bit more about that when the actual tool is running. The third tool in my program is the drill. This is an 1.25 inch inserted drill. We're using TSC on this one. Again, we programmed that right at 540 surface feet per minute and feeding at 6 thou and 1/10 feed per revolution on that tool. The last tool is the chamfer tool. I've got the 2-flute 45-degree chamfer tool here. This one's programmed at 800 surface feet, quite a bit faster. It's taking a much smaller cut, and we've got 7.5 thousandths feed per tooth for those 2 tooth, and that's just to put a 50 thousandths chamfer on all the sharp edges on this demo program.
And actually, you just did a video on chamfer mills. We just released that on YouTube. So if you haven't seen it, check it out. Okay, are we ready for the demo?
I think we are.
Tyler, you want to come in and we'll get you in here tight? So we're going to have Tyler come in and get a close-up, and then we've got a camera inside the machine.
I'll mention one thing real quick. In the demo program, I used a little macro statement to zero out the spindle load meters for each tool before they run, and then it'll record the maximum spindle load that tool achieved during the cut. I've got all of that information being deprinted to a file, and we can take a quick look at that at the end of the demo, and then we'll relate that spindle load information to the torque chart next.
Perfect.
All right?
Okay.
So this cutter's coming in. It's taken 150 thousandths depth of cut and a 2-inch width of cut. My spindle load meter is hovering around 130. You can see the chips coming off there are nice straw colored, and as they hit in the pan, they turn a little bit blue. That means we're cutting just perfectly. Here's the end mill. So this is a 1.5 times diameter deep. This is 1 inch, 125 deep. And I'm taking a 33% of the diameter width of cut, which is 250 thousandths on that 3/4 inch end mill. So 1 inch, 125 deep, and 250 width of cut. We'll take a couple of cuts. And again, you can see that the chips are coming off straw colored or a little bit blue, and when they hit the pan they turn real blue. That means all the heat in the cut is coming out in the chip. This thing's cutting really well.
And what kind of spindle loads do we have?
Spindle load is 75%.
Okay, so you've got some room if you want to.
I've definitely got room to optimize.
Bit.
I could increase my width of cut and take a bigger spindle load because I've got the headroom there. Do a little cleanup pass here just to
make it look nice.
I was wondering if you could get a shot of the chips over there on the way cover. I'll hold this. You can see the color of the chips, how they're nice and blue. The thinner chips, which didn't carry as much heat out, are straw colored, and then the bigger, thicker chips have turned blue because all the heat in the cut has come out in that chip and not in the workpiece or the material. Okay, I'm going to focus back on our part and I'll continue. So that's an 1.25 inch inserted drill going through 3 inches of material. My spindle load is 95%. It's fluctuating a tiny bit right around there, but that's perfect. Right at 100%, 110%, 120%. We can do that all day long with that tool.
And you definitely want through spindle coolant with this tool. You got to get those chips out of there.
Yeah, definitely. Unless you're doing a very shallow hole, you've got to have through spindle coolant with these insert drills. We'll toss 3 holes in there.
So one of the things we talked about was spindle load, and you say you feel comfortable running that all day long. It's always a balance, right, between tool life and how fast you're removing material?
Yeah, absolutely. So With regard to spindle load, so the vector drive and Haas machines will allow you to run below 150% continuously, right? All day long in that cut. At 150%, we can go continuous for about 30 minutes still before we are, run into trouble with maybe overheating the spindle motor.
Right.
And even if you bury this thing at 200% spindle load, you've still got about 3 minutes of cut time to get away with it. So there's still plenty of headroom utilizing the vector drive in our machines.
Right. But at some point, you're going to be compromising tool life, right?
Yes, absolutely. You don't want to push things too hard not because the machine can't take it,
right,
because the tooling can't take it. The last thing you want, if you make parts for a living, the last thing you want is a catastrophic tool failure because you lose the tool, you lose the part, it's a mess.
Right.
And so reasonable spindle loads for your cut and your tooling, in my opinion, hover around 100, 125%. I wouldn't try to go too much more than that on a regular basis. Backing off of there is definitely going to give you longer tool life.
Right.
And it's not that it injures the machine or anything, it's more about the tooling.
That's right. Yeah, when I used to, in my previous role here, I used to go to a lot of customer shops, and guys would be running their machines at 30, 40% spindle load, thinking that was going to make them last longer.
Yeah.
And it probably did, but you're leaving money on the table.
Yeah,
when you're doing
for
that.
sure. You're sure. The extra time, cycle time that it takes to machine at those lower spindle loads is costing you money.
Exactly.
For sure. So I wanted to take a quick look. I'll show you the dprint file here that I created. So at the end of this program, I wrote the maximum spindle load recorded by each tool. So tool 1 had a maximum load of 151%. Tool 2, which was the 3/4 inch end mill, did 83% at a maximum. The drill was 111%, and our chamfer tool was only 5% spindle load. So you get an idea of where those loads came out, right? Well, 150 for the face mill, 83, 85 for the end mill, and then 111 for the drill. Now let's pull up the torque charts and see how that information jives.
Hey, look, I got it right here for you. All right, I'm going to scoot over here just a little bit.
So when we were preparing here, I recorded 155% spindle load on that face mill the first time through. You can see that the maximum torque is up here at 90, and that's 200% spindle load. You can see we talk about that here. The values shown for horsepower and for torque are at 200% of the load of the spindle motor. So our cut was 155% of that spindle load. When I take 155 and divide it by 200, I get 0.775, 77.5%. That's my conversion factor. So at the RPM I was running, 10,082, I have right at 90 foot-pounds of torque. So 90 times 0.775 gives me 70 foot-pounds of torque. So that's the torque value that I pulled, 70 foot-pounds at 155% spindle load. Now let's pull up the next chart. This is the 3/4 inch end mill, and that was running at 2929 RPM, 2,929 RPM. So my torque value is a lot lower here because the chart has come down. So at this RPM, I have less available torque. I pulled an 84% spindle load and did the math on that, and that showed me that that end mill was requiring 35 foot-pounds of torque, and this is where that 35 foot-pounds falls in. Remember, this is my maximum, not that, when I'm making this calculation. And then the last tool...
So you actually, in this case, you had quite a bit. You have a huge headroom in terms of running that tool harder, but
yes,
you probably don't want to run it that much harder.
Right. I would take, in that case, I was taking 250 thousandths width of cut and 1.5 times diameter deep. So I would ease that width of cut in if I needed to remove more stock per cut. That's how I would utilize the available spindle load that I have on that tool, and I'm probably not going to harm that tool or cut its life down at all by increasing that width of cut.
Right. When we were kind of preparing for this, you were talking about how one of the things you like to do is kind of start, if you're unsure about what spindle load you want to use, you'll come in and kind of start light,
yeah,
and then see where that puts you and then do the calculation.
Yeah, absolutely. So the way I would approach it if I was unsure about the cut I wanted to take, I would get the speed and feed information for the cutting tool and use that right in the middle of the speed and right in the middle of the feed rate information, and then go ahead and take a light depth of cut, right? Set up your cut with the width you want, but take a lighter depth. And then, for example, let's say you took that light depth of cut and you had a 50% spindle load. Well, if you change one cutting parameter, like depth of cut only, you can double that depth of cut and your spindle load is going to double. So you go from 50% spindle load up to 100, so you can take that, that cut, you know, twice. So you take twice the original cut. You're going to double the cut, it'll double the spindle load on you. So that's how taking a light cut, monitoring the spindle load and seeing how much available torque you've got or headroom you've got on spindle power, and then go from there as far as adjusting and optimizing your cutting parameters. But definitely go with the recommended speed and feed and adjust your cut parameters as far as depth or width of cut.
Right, right. It's just a practical, like, empirical way to quickly get to a good value without maybe doing some involved, power calculate or something. You just start off at the recommended values and
definitely. There's also milling and turning calculators on the control where you can punch in your numbers and it'll give you a rough value for required power based on what material you choose on that calculator.
Right. Okay, so third tool.
The third tool here was the drill. We can see that was running at 1,650 RPM, where we're back up in our maximum torque range to see, but we pulled 110% spindle load, right? 110% divided by 200 gives me my percentage, which I multiplied by the 90% foot-pounds, and the percentage was 0.55 actually. So 55% of 90 foot-pounds of torque is 50 foot-pounds of torque. So that's what that cut pulled, and I was definitely right in the sweet spot for that tool at 100%, 110% spindle load.
Cool.
So that's how you kind of translate the spindle load numbers to the torque chart and figure it out.
Right, you have all that information on the, you know what your spindle load is from the machine, you have this information on the website or any other, any other place you're getting your tooling, and it's easy to get started.
Yeah.
Cool. Thank you, John.
All right.
I think that's it for this machine.